Okay. So I handed out, first of all, what I anticipate to be the reading and problem assignment, whatever we finish up today. If we don't get through all of that, we will pick that up tomorrow, but that way, what I did was I broke the top hat problems up according to section, so that way you know which ones go with which of the sections. And then you have the packet with the notes I'm going to talk about today, as well as a summary of SN1E1 and SN2. We're going to do SN2 reactions today, and then some problems. And so I anticipate today we're going to talk about the first mechanism, which is SN2, and then we're going to talk about SN1 tomorrow, and then it's E1 and E2. So this week, that's what we're going to be going over, SN1, SN2, E1, and E2. So first of all, we're going to have to define what these terms mean. So let's go to the notes, and let's talk about kind of what we did last week at the end of Thursday, and then put it in context of what we're going to do in terms of substitution. So last week what we talked about was, we talked about what is a nucleophile, what is an electrophile, and so the nucleophile was electron rich, the electrophile was electron poor. There are degrees of that. The extreme degree is that the nucleophile has a -1 charge, and the extreme for poorness is that the electrophile has a full-blown positive charge. In between, so nucleophiles with a negative charge, we're going to call a strong nucleophile. So a strong nucleophile is one that has a negative charge. And a strong electrophile is going to be one that has a positive charge. But we can actually have in between, so we could have, for instance, we could look at water, and water doesn't have a negative charge, but it does have electron richness in terms of its lone pair. So HOH, water, HOR, where the R group is any alkyl group, and alcohol. These are going to be examples of neutral nucleophiles, since they have electrons as lone pairs, but they don't have a negative charge. And we're going to call those weak. So anything with lone pairs, but not a negative charge, is going to be called a weak nucleophile. And strong nucleophiles are going to react slightly different than weak ones. But I'm going to break down those two terms simply in terms of a negative charge versus no negative charge. Okay, so I'm kind of oversimplifying, but to start with, that's the easiest way to go. Then if you talk about electrophiles, an electrophile with a positive charge is going to be something like a proton, or we are going to find tomorrow that a carbon that only has 3 bonds attached to it also has a positive charge, and this is what we call a carbocation. And these are both examples of very strong electrophiles because they have a positive charge. Other things that are kind of neutral but still electrophiles would be if I took a carbon and I attached it to a halogen like Br. The Br would be slightly negative and the carbon would be slightly positive. So this would still be an electrophilic carbon because it is electron poor, but it doesn't have a full-blown positive charge. So we have these extreme cases of charged species, and we have the kind of in-between where they don't have a full-blown charge, but they're still either electrophiles or nucleophiles. Okay. Now we'll get to carbocations tomorrow, But we're going to start with the idea of a strong nucleophile with a negative charge. And we're going to start with this idea of a carbon attached to a halogen as the electrophile. And so that's the first reaction we're going to talk about. So if I took a nucleophile, let's just say I took like a hydroxide ion, and I reacted it with something like bromomethane or methyl bromide, I can actually have a reaction occur, and it's going to be a substitution reaction. So what's going to happen is that this carbon is slightly positive, that bromine is slightly negative. The pair of electrons on the oxygen that's giving it the negative charge is going to come in, and I'm going to form a bond between that oxygen and that carbon. Okay. And we always use curved arrows to show the movements of electrons. So when you have a curved arrow, this means 2 electrons, so it's a pair of electrons. There are half arrows, but we'll get to those next in the next class, meaning second semester, the way that this book is structured. So this means 2 electrons, and the arrow is always showing where the electrons are moving to, which means your positive or your delta positive side is always where the head of the arrow is. And then your negative species, usually your nucleophile, is to the left. So your nucleophile with either the negative charge or the pair of electrons is always on the end of that arrow. So arrows always move to a positive charge. And so in this case, that's what this arrow is doing, is moving towards this positive charge, delta positive on the carbon. So that hydroxide is going to donate a pair of electrons to the carbon. But if it does that and nothing else happens, the carbon is in trouble because it would have 10 electrons and it can't form an expanded octet. So at the same time that the oxygen is giving pairs of electrons to form a new bond, this carbon-bromine bond is breaking, and you could already say, well, you could already say that the bromine has a good chunk of the electrons from that carbon anyway, because it was delta minus, and that's what was making the carbon delta plus to begin with. So as the hydroxide comes in, the bromine gets kicked out. And so in the end, I'm going to have my OH attached to my CH3, and I'm going to have the Br minus then as its own group. So this is what's called nucleophilic substitution. And the reason it's called nucleophilic substitution is, number one, it's a substitution reaction. I'm substituting for the bromine an OH. I'm substituting one nucleophile in terms of it being electron-rich OH minus, and I'm forming a nucleophile on the other side. So this is substitution with a nucleophile forming another nucleophile. So this is what we call nucleophilic substitution. And so abbreviating that, it's substitution nucleophilic, so S with a small n. And this is the simplest type of substitution that we can have with a nucleophile. So the nucleophile has to react with a carbon that has something that can leave attached to it. And so there's one other term I'm going to add, and that is this group that's leaving is called the leaving group. So that we're going to start with halogens as the leaving group. So the nucleophile is going to replace the leaving group. And then on the other side of the reaction, that leaving group then is a nucleophile. So in theory, we could have an equilibrium reaction occur where the hydroxide comes in, kicks off the bromine, and then the bromine could turn around and kick off the hydroxide, but actually we're going to find out that that doesn't happen. And so we're going to have to talk about the strengths of leaving group. What makes a strong leaving group versus a weak leaving group? What makes a strong nucleophile versus a weak nucleophile? And we've already kind of defined that up here by saying that if you're a nucleophile with a negative charge, you're strong, and if you're neutral, you're weak. But there's other things that go into this. That's sort of the first cut. What if we have two negatively charged nucleophiles? Which one's stronger? So we're going to have to go to that, and we'll have to look at the periodic table. Okay. So that's nucleophilic substitution. And now we need to get into the gory details of how this occurs step by step, which is called a reaction mechanism. Right? So if you look at this, then this is just showing the idea that a nucleophile will come in, add its pair bonds to that carbon, and kick off the halogen so that we end up with our substitution reaction. So I'm going to skip ahead a slide. And again, this shows the same thing. Now I'm saying this nucleophile, the carbon's delta positive, and the halogen is slightly negative. And that's what creates the nucleophile electrophile coupling. All right, so let's look at sort of a picture of this. The first question that we have to ask is, well, there's a number of questions that we need to ask. But the first question that was asked was, how does this nucleophile form a bond with the carbon and then the halogen gets kicked off? And one of the ways that people propose, there's two different mechanisms you could think of. You could think of, and I'm going to jump back here for a moment, that the carbon, or that the nucleophile comes in and it attacks from the backside of that carbon, kicking off the halogen. That's what's called backside attack. But you could also say that maybe the nucleophile comes from the front side and adds and kicks off the halogen, and that's called then front side attack. So the first thing that we have to do with this mechanism is we've got to figure out, does this occur by backside attack? Does it occur by front side attack? Or maybe it's 50-50, or maybe it's some of both. And so this is a relatively straightforward problem to solve. What you do is you say, well, okay, I'm going to get my hands on some 2-chlorobutane that is optically active. So in other words, it's the pure enantiomer of either the R or the S. And in this case, what would the chiral center of this carbon, what would it be? Would it be R or would it be S, the way I've drawn it? Yes, R? So chlorine, ethyl, methyl, the hydrogen's pointing back, that's why I put it there. So this is the R configuration. So let's say we get this, we know what the rotation is. The rotation could either be positive or negative. Again, there's no direct correlation between R and D and L because some R's are D, some R's are L. But for this one, we would know what that correlation is. And now I take my hydroxide and I say, okay, let's react the hydroxide with the carbon and kick off the chlorine from the backside. What happens from the backside is that the hydroxide comes down the carbon-chlorine bond so that it ends up in the plane. The CH3 then still stays in the plane. The H ends up behind, and the CH2CH3 ends up bold, and we end up with then our Cl minus over on the other side. Now notice that when the hydroxide does a backside attack, these groups that are attached to the carbon go from being oriented to the left to being oriented to the right. It's one of the examples you can kind of think of is that, and this doesn't necessarily work out all that well, but this is kind of like these groups are an umbrella being blown like inside out. They go from being oriented to the left to being then blown inside out on the other side. But if backside attack occurs, what is the configuration of the carbon product? Is it R or is it S? Now the hydroxide is number 1. So going 1, ethyl 2, methyl 3. It's clockwise because S is, or the hydride's away from you, hydrogen. So now I have the S configuration. So for backside attack, the R would become S. And I could determine that because I could look at tables and say, well, my S2 butanol is either D or L. And so if I do this experiment, I'm going to get the optical rotation. I'm going to determine the configuration from that. So if we went from R to S, then we know it's backside attack. If it's front side attack, then you could imagine what happens. What happens to the configuration if the hydroxide comes in and adds to the front and basically takes the same position as the leaving group? It's going to be the same configuration. So in the end, R stays as R. So people didn't know which one of these occurred at the beginning. And this is the experiment they designed to determine, does the reaction occur front side, does it occur back side? Of course, if it occurred 50-50, 50% front side, 50% back side, then I would end up with a 0 rotation because I'd end up with 50% S and 50% R. So they did this experiment. What they found was that when they did this type of an experiment, they always got 100% inversion of configuration. And so the chiral center was always inverted. R became S and S became R. So that led them to the conclusion then that this reaction must occur by backside attack and that there's no front side attack. So that's the first thing that we learned about this reaction. And this reaction meaning that this carbon is either a primary or a secondary carbon. Now what does that mean? Remember, primary carbons just have one other carbon attached to them. Secondaries would have two carbons attached to them. Tertiaries would have three. Halogen doesn't count. So this would be a CH2 group or a CH with two other alkyl groups attached to it. And so they found that when they took a primary or secondary carbon, they got backside attack. So that's the first thing we know about SN2, what we know about this SN reaction. We'll get to what the 2 means in a moment. So let me add a new blank slide here. We now know why that's the case. And in the book, for this chapter, I don't know if I skipped over the molecular orbital diagrams, but you can. Because I'll show you what we know. What we know is that our nucleophile has its pair of electrons in an orbital, like an sp3 hybridized orbital. And the carbon then is also sp3 hybridized when there's 4 groups attached to it. So it's also sp3 hybridized. And then the halogens are sp3 hybridized. Only 3 of its orbitals have lone pairs. Now this is one of these cases where we're going to invoke the little teeny tiny orbital that's on the other side of the big sp3 hybridized orbital. So remember that for an sp3 hybridized orbital, when we talked about this like 2 weeks ago, that we had that as our sp3, that was our sp3 hybrid orbital, with this little teeny tiny lobe and then the big lobe. And I said, we're going to forget about the little teeny tiny lobe for the moment, but we'll come back and we'll invoke it in certain cases. This is one of those certain cases. So what happens is there's a little teeny tiny lobe on the back side of that carbon. And so that's how the nucleophile comes in, and it overlaps with that teeny tiny orbital. And then as this halogen takes away the electron density from the bigger orbital, the electron density shifts over, so that at the end we've got the nucleophile now with an sp3 hybrid orbital to that carbon, and then it has its own little teeny tiny orbital on the other side. So because when we make and break bonds, we're overlapping orbitals, it has to occur from the back side. The nucleophile has to attack from the back side because that's where that little teeny tiny orbital is for it to overlap. There is no orbital on the front side for the reaction. So by doing the experiments with the chiral molecules, and that's why we needed to know chirality first in chapter 6 before we got to chapter 7, or whatever chapter we're on. What chapter are we on? 7. That's why we needed to know the chirality, because we need to apply the correct chirality in order to determine whether a reaction is front side or back side attack. So we now know that this substitution with a primary or secondary halogen is backside attack, not front side attack. Okay. Does that make sense? So that means that if I'm looking at the molecule, the nucleophile then is going to attack on the backside directly down the carbon-halogen bond. Now, what happens with the energy of this reaction is, if I plot energy versus what I call reaction progress. So in other words, going from reactants to products left to right. I start with my reactants. I end up with my products. On my energy diagram, whether the reactants have the same energy of the products is a question of whether the reaction is endothermic or exothermic. If it takes energy to form the products, then it's endothermic. If it gives off energy in the reaction, it's exothermic, and we'll come back to those terms. But what happens? Well, what happens is as this nucleophile with its negative charge comes closer and closer to that carbon, the energy goes up until it reaches a maximum, and then it goes back down again. So in the bond making and the bond breaking process, because this is going to be our first reaction that we've done, in that making and breaking of the bond, you're going to have the energy go up to a maximum and then go back down to wherever the products are. And there may be this is just a single hump, we may have to write double and triple humps. So we're going to have a peak and a valley. We'll get to what the valley is tomorrow. Okay. So here's my peak. So what is that peak? That peak is the highest energy of the reaction. And if we went back to general chemistry and we looked at the reaction coordinate diagram, there are some basic fundamental things in here that we learned about back in general chem, like if you have reactants and you have products and the reactants give off, so if there's energy given off in the process, that's going to be an exothermic reaction, not endothermic. That's going to be an exothermic reaction because energy is given off. If the reactants going to products takes energy, so I had to add energy to that process, that's going to be an endothermic process. So if the products have higher energy than the reactants, it's endo. If the products have less energy than the reactant, it's exo. And since energy is going up on this diagram, we're going to have to remember that the lower the molecule is in energy, the more or less stable is it. So in other words, if one molecule is lower in energy than the other, is it more stable or is it less stable? About. So I'm asking the question, if I have a reaction coordinate diagram and I have a species here and a species here, so I have A and B, and the energy is going up, so A has more energy than B, which one is more stable, A or B? What did I hear? B? So B is more stable? Do we agree with that? So that's true. No, you're right. B is more stable. B is more stable. So a species with less energy is more stable. Which one is more reactive? We agree it's A? Right. So A, having more energy, is more reactive, and B is more stable because it has less energy. Right. I mean, within reason, you could apply this not only to chemistry, but you could probably apply this to people. Right? You have to know, if you are not that person, you have to know somebody who would fit those characteristics. Having a lot of energy, well, we could reverse it and say the more stable you are, the less reactive you are, the more unstable you are, the more reactive you are. That's usually how it gets applied to people. But that's what we're doing here. So with these diagrams, we have to have the fundamentals down. And the fundamentals are the lower you are in energy, the more stable you are, and vice versa. Now, when we're looking at this energy diagram, what is this energy? What is the energy that it takes to go over that peak and go to the other side, which is to form the products? We usually talk about it in terms of kinetics, in how fast the reaction goes. General chemistry, come and gone. It's the activation energy. So this is EA, which is the activation energy. So the activation energy is what it's going to take me to get over that barrier to form my bonds, to break and make bonds. So every time we break or make a bond, we're going to have to go over an activation energy barrier. And we'll talk in gory detail about that in a while. Okay. Don't know how well the next question is going to go, but what is the species at the top of the peak? What's it called? The actual species itself. The transition state. So that's a transition state, which is sometimes abbreviated as a double dagger. Dagger. This is a double dagger. So the transition state is a species that has such high energy that it only exists for a split second. I can't put a transition state in a bottle and study it. Probably the only place I can study a transition state is on the computer, because it's not necessarily a real species. It is real from the standpoint that it exists, but it only exists for a very short time because it's such high energy. And the transition state is where the bonds are going to be made and broken. Sometimes made, sometimes broken, sometimes both. In this case, it's both. So in this case, the transition state, I'm going to be making a bond and breaking a bond at the same time. So we need to know those terms on our reaction coordinate diagram, on our energy diagram. We need to know what those terms mean. The activation energy is important because if I don't have that level of activation energy, I'm not going to make it over the mountain. And I'm going to talk about hikers going over the mountain. I'm going to talk about birds flying over the mountain. I'm going to talk about birds and hikers near death. They're not going to be able to make it over the mountain, or supersonic birds that can fly over any mountain no matter how high it is. but that'll be later. So that's the coordinate diagram that we have to know. Now, and this is actually was all in chapter 3. But what happens is that we read chapter 3, then we go to 4, 5, and 6. We forgot about chapter 3, and then we end up relearning it now. So we skip through the middleman and just jump to it now. But this is all described again in chapter 3 as well. All right, so what does it have to do with this reaction? Well, I'm going to make the nucleophile carbon bond, and I'm going to break the carbon electrophile bond. And there is a question here about, does that happen at the same time? Or do I lose the halogen first and then the nucleophile comes in? And that's going to be a question of kinetics. So what we're going to do is let's skip ahead to the kinetics, which is this slide. Let's examine the kinetics of the SN2 reaction. And you might say, where did the 2 come from? Well, the 2 came from kinetics, so let's talk about where the 2 comes from. Back in general chemistry, how did you determine what the overall rate equation is for a reaction? If you don't remember that, here's how it's done. What we do is we take the concentration. We have 2 reactants here, nucleophile, alkyl halide. If I double the concentration of the nucleophile, well, hold on. I take 1 times the I take a concentration of the nucleophile and a concentration of the electrophile or the Rx, and I measure a rate of reaction. Now, let's say that rate of reaction, just for the sake of argument, is 1. So if I took 1 molar nucleophile and 1 molar Rx, I get a rate of 1. And in general chemistry, you would have gotten a whole table of these values. And what they would have done is they would have said, okay, now let's use a 2 molar concentration of nucleophile, a 1 molar concentration of alkyl halide. Let's measure the rate, and the rate is 2. So what does that mean? When I double the concentration of nucleophile, the rate doubles. And I hold the concentration of alkyl halide constant. Then I would say I'm going to hold the concentration of nucleophile at constant at 1. I'm going to use 2 times the concentration of alkyl halide, and the rate doubles. So when I doubled the concentration of nucleophile, the rate doubled. When I doubled the concentration of alkyl halide, the rate doubled. So then I can write a rate equation. Rate equals some rate constant times concentration of nucleophile times concentration of Rx, both of those being the reactants. And so what does it mean that when I doubled the rate, doubled the concentration, the rate doubled? That means that up here there's a 1. And over here is a 1. What's the significance of this 1? If you double the concentration of a reactant and the rate doubles, we say that that reaction is something in that reactant. First order, right? So this means that it's first order in nucleophile and it's first order in alkyl halide. if a mechanism is such that I double the concentration of nucleophile and the rate goes up 4 times, so if you double the concentration and the rate increases by a factor of 4, that means there should be a 2 here, because 2 squared is 4. And so that would be a second order reaction in nucleophile. But what we find experimentally is that it's first order in nucleophile, first order in alkyl halide. So then I would say this reaction overall is second order. So in other words, I add the 2 first orders and get a second order. So overall then, this reaction is second order. Now, when I teach general chemistry, which isn't all that often, I think the last time I taught it was in 2010. Then the last time I taught it was 2001. But when I first started here, I taught it general chem, organic, every year, both of them. So I would see the same students for 4 semesters straight, which may have been good or may have been bad, depends on them. Right? But when I would talk about this, I would say, okay, we need to know this order because that's going to tell us how the reaction occurs. So I can only get these orders from experimental data. So I actually have to go to the lab and do the experiments in order to get the overall rate equation in terms of it being first or second order. There is no way for me to get this by looking at it. Okay. And how would you look at it how would you determine that by looking at it? Well, this would be wrong, okay, wrong. If you use the coefficients, that's wrong, because sometimes the coefficients match up and sometimes they don't. So you have to go to the lab and figure out what the rate equation is. So in this case, they said it was overall a second order reaction. It was first order in nucleophile, first order in alkyl halide. And you may say, who cares? Well, first thing we care about is that's what this 2 means. This 2 means it's a second order nucleophilic substitution reaction. But there's something more important about this. And that is that if a reaction of A and B to make whatever it's making, if the rate equation is equal to K times the concentration of A to the first power times the concentration of B to the first power, that means that we need to define something before we say what it's in. What do I have to define? Well, remember, this is the overall reaction up here. What is the step-by-step description of how the reaction occurs? If I want to talk about how it occurs step by step, that's the reaction mechanism. So, in a reaction mechanism, your best case scenario is you choose the simplest mechanism you can. Least number of steps with species that you can determine whether they exist or not. When you end up with a reaction that's first order in both of these reactants, what it most likely means is that it's a one-step mechanism. So if this was a one-step mechanism, A reacts with B, so this is what we call a mechanistic step. If A reacts with B to make whatever it is, then we can actually write the rate equation of each of the mechanistic steps. Bless you. And if we do that, so for a mechanistic step, not an overall reaction, but a mechanistic step, I can actually do this. I can write the rate of that mechanistic step using the coefficients. Now wait, you just said you can't write the mechanism for, or you can't write the rate equation from the coefficients. Yes, you cannot do that for an overall reaction. But as you're trying to write down what steps it can undergo, you are allowed to write the rate equation for each mechanistic step. And so if I assume that this reaction is the simplest of all mechanisms, A reacts with B, then that means its rate equation would be 1A reacting with 1B, so its rate would be A to the first, B to the first. And so now what we do is now we take these ones and they now actually represent molecules. So that one molecule of A reacts with one molecule of B. So if that's a mechanistic step, if that's a true mechanistic step, then its rate would be K times A to the first, B to the first, and one molecule of A would react with one molecule of B. Well, what do we have here? We have this mechanistic step. We're saying that the rate was nucleophile to the first, alkyl halide to the first. So if I'm going to write the simplest mechanism I can, I'm going to say that is the mechanistic step. It's one step. One nucleophile reacting with one alkyl halide. It's going to give me the same rate equation as the overall rate equation from the stoichiometry. And since that rate equation, or since that mechanistic equation equals the overall rate equation, then that must be the slowest step in the mechanism, right? The rate determining step, which we'll talk about tomorrow. But in this case, if there's only one step, it's the slowest step. So when people did this reaction, they went through this analysis and said, let's propose the simplest mechanism. There's something out there called Occam's razor. Right? Occam's razor says the most likely conclusion is the one that's the simplest. Right? Occam's razor works particularly well with conspiracies. Right? Because simple conspiracies are pretty boring. It's the elaborate ones, and that kind of cuts against Occam's razor. Well, if we're doing mechanisms, we assume that chemistry really doesn't want to go through the most complicated mechanism. It wants to go through the simplest one. Why? Because the more complicated it is, the more energy it takes, and chemistry is all about minimum energy. Minimum energy I'm going to have to take in, minimum energy, that I'm going to give out. So in this case, what people have determined is that for this equation then, that mechanism, it's a one-step mechanism. Because the mechanism has the same rate equation as the overall rate equation. And to be honest with you, that's kind of what we've been assuming here. So we're assuming one nucleophile comes in and reacts with one alkyl halide. Now, that is what is called a bimolecular. That is a bimolecular reaction. A bimolecular is a second order reaction because two molecules are colliding in the mechanism. So the nucleophile is going to come in, kick off the chlorine or the bromine. One step. Now, when a reaction is one step, it is also called a concerted mechanism. So a concerted mechanism is a one-step mechanism. So the reason we're starting out with SN2 today, first of all, that 2 means either the overall rate equation or that this is a bimolecular reaction. So this is actually bimolecular nucleophilic substitution. It's concerted, meaning it's one step. And so in a concerted mechanism, you're making and breaking the bonds at the same time. And that's kind of how we've described this reaction. I'm making the nucleophile carbon bond, and I'm breaking the carbon leaving group bond. The only question is, what does the transition state look like? If it's one step, I got to form, break the bonds at the same time. So what is the species at the top of that peak? What's it look like? What's the transition state look like? And so we can imagine the transition state looking like this. So where the groups over here are pointing to the right, and then over here after the reaction they're pointing to the left, your left, and my left. And then at the end of the reaction they're pointing to the right. What would be in between? In between would be having these three groups dead in the center. With a partial bond to the nucleophile and a partial bond to the halogen. The nucleophile is starting to give up some of its electron density to the carbon to form the bond. The halogen is taking away its electron density from the nucleophile because it's going to get it from somebody else. And so we have a partial bond, dotted line, that represents a partial bond, just like it did with resonance hybrids. And nucleophile and the halogen are going to be slightly negative because each one doesn't have a full-blown positive charge yet. So that's what the transition state will look like. Those groups will be right in the middle, partial bond to carbon, partial bond of carbon to nucleophile, partial bond of carbon to my leaving group, my halogen. And so what does that look like? It looks like this at the bottom. So when you look at that, what you see is the nucleophile and the halogen and the other three groups, it's a trigonal bipyramidal geometry. Because it has 5 things attached to it. Now if you go back and you say, but wait, you told us that the number 2 biggest mistake you can make in organic chemistry is more than 4 bonds to a carbon. True. But in this case, the bonds between the nucleophile and the halogen, they're not a full 1 bond. Between the 2 of them, they're 1 bond. So the carbon still only has 4 bonds. It's got a partial bond to the nucleophile and a partial bond to the halogen. If those were 5 full bonds to that carbon, I mean, we'd be in Nobel Prize territory. Because we've violated rule number 2. And we'll get to rule number 3 tomorrow. Rule number 1, of course, is taking it, but there's nothing you can do about that. So that's what the transition state looks for this SN2 reaction. It's trigonal bipyramidal. The groups are on their way from being oriented to the left to orient it to the right. The nucleophile is on its way in to form a bond, the halogen is on its way out. And again, when people developed this idea of SN2, they had to go through all these steps. They had to go through the kinetics first. Oh, well, the kinetics are first order in these two things. What does that mean? Well, I'm going to propose a simple mechanism. So if I propose my simple mechanism, is it front side, is it back side attack? Well, chirality says it's back side attack. So now everything is based on that, the idea of this transition state. Can I ever put this transition state in the bottle and study it? No, I can't. But it makes sense. And so that transition state is what is at the top of the energy diagram. Okay. All right, so is everybody still with me? So for SN2, we've got a bimolecular kinetics. We've got a transition state that's trigonal bipyramidal. The reaction goes by inversion of configuration. And the only other thing that we really have left is let's classify alkyl halides and say, now which ones of these can undergo this reaction, this mechanism. So one of the things that we have here is we've got primary alkyl halides where the carbon attached to the halogen or attached to the leaving group is a primary carbon, meaning it's got one other carbon attached to it, or secondary or tertiary. When the halogen is attached to the double bond, that's called a vinylic halide. So that's where the term vinyl comes from. Right? Anything that's made of vinyl, its precursor is a molecule like this. If this was a chloride, that would be vinyl chloride that we would make polyvinyl chloride out of, or PVC, which could either be an album, like a music album. They're sort of on their way back. I don't know why. And I still have my stereo system from the 90s, but it's not as rich as digital. But I still have it. You can still go buy your vinyl discs. Why they call them vinyl? Because they were made of polyvinyl chloride. Your white tubing that you use for plumbing is polyvinyl chloride with a ton of titanium dioxide in it to make it white. Benzylic halides, where you've got this circle, which I really shouldn't have in here, but the circle represents 3 alternating double and single bonds. So a benzylic halide has a benzene ring attached to the halogen. Now these two do not undergo SN2. And they will not undergo SN1 that we'll talk about tomorrow. So they're only here just to say we're not going to worry about those because they don't react in either mechanism. I'm only concerned about primary, secondary, and tertiary. So one of the things I see on this slide then, because it's letting the cat out of the bag, that primary alkyl halides react the fastest, secondaries react second fastest, and alkyl halides undergo no SN1 or no SN2 reaction. So why is that? It's all about steric hindrance. So if what I've told you so far is true, and it better be, right? Because you can't go back and redo all of this. But if that mechanism is true, then the less steric hindrance you have around the carbon that's being attacked, the faster the reaction will occur. The more steric hindrance you put around it, the slower the reaction is going to be. So if you had a primary alkyl halide like this The carbon that's being attacked is in this burgundy color. And so if you're the nucleophile looking at that, you can relatively easily get to that carbon, get to the transition state, kick off the leaving group. But if we go to a secondary halide, you can see that getting to that carbon as the nucleophile is more difficult. So what's that going to mean? It's going to mean that it's going to take more energy. If it's going to take more energy, what's it going to take? More time. So that reaction is going to go slower. Slower than a primary at exactly the same temperature. And then if you go to a tertiary halide, let me go, that's one slide ahead. If we go to the tertiary halide that has 3 methyl groups around here, now you can see I really can't get to that carbon, and if I can't attack that carbon, then I can't undergo SN2. So now the steric hindrance is too much. And you might even make the case that if we go back a slide, if I put a terse butyl group and a methyl group on the carbon so that that carbon is still, it's a secondary carbon, but it's got a big, huge, bulky tertiary group, you can see that basically I'm going to have a very difficult time getting to that carbon because the terse butyl group is going to block it. So SN2 then is, since it's based on the backside attack of the nucleophile, steric hindrance is going to be the critical part. That's a good question. So, usually a good exam question. Because, well, it's a good exam question because what, if I wanted to know that for a fact, this carbon has a methyl, a T-butyl, a halogen, and a hydrogen on it. So if I wanted to know if this could occur by SN2, what I would do is I would get the chiral version of that and do the reaction. If I saw any inversion of configuration, that had to come from an SN2 mechanism. Now you might say, why don't you just look for final product? Because tomorrow we're going to talk about the competing mechanism which this reaction might undergo. And so if this reaction undergoes that competing reaction, I'm actually going to get a racemic mixture of the two products. So in this case, I don't know. It would actually be an interesting experiment to do this, to get it chiral and to see what I get out. I'm going to probably have to raise the temperature on it though to get it to go backside. And if I raise the temperature, the other competing reaction is probably going to increase as well. So if you look at some of the older exams, which will be for next Monday, if you look at those, you'll occasionally see where I ask a question about, well, this particular reaction, the student wants to know if it's SN1 or SN2, what should they do? The first thing they should do is measure the rate of the reaction. Because if it's bimolecular, then yes, it's going by that. If it's not bimolecular, it's going by a competing mechanism. And you could look at the chiral, or the enantiomers that are formed. So the answer is I don't know. I just use it here because if I'm the nucleophile, it's awfully tough to get to that carbon. Then there'd be another, if the competing reaction occurs, then there's another complication to it. Okay. So now we have this. So now we have these sterics. So for SN2 reactions, we're only going to use primary and secondary halides. So that's what we're going to talk about. Now, if I skip all the way to the end here, here are the important things for SN2. And these are important simply from the standpoint of when I do the competing reaction tomorrow, we're going to compare and contrast SN1, which is tomorrow, to SN2, which was today, including writing the mechanisms ourselves and talking about the rate, how solvent affects and how the what makes good leaving group and a good nucleophile. Right. So that's